Hi, I'm Dylan Burns.
I'm Hunter Meisner.
My name is Jesse Poirier.
I'm Jack Sweat.
My name is Steven Usher. We are C Team 14, and our project is FoamSat.
Hi, I'm Ryan McDevitt. I'm the CEO of Benchmark Space Systems. I'm the industrial mentor for this project, and we're also the client.
My name is Darren Hitt. I'm the director of the Vermont Space Grant Consortium, who is providing the funding for this project. I'm also serving as a faculty mentor for the project.
The goal of this project is to create a propulsive attitude control system which can be incorporated in 1U of a 3U CubeSat architecture.
A CubeSat is a design standard for a class of nanosatellites designed to enable low-cost research and commercial endeavors. Current technologies offer precise orientation control through reaction control wheels and magnetorquers, but do not address translational positioning. This requires an onboard propulsion system.
In the past, propulsion systems have not been incorporated on CubeSat architectures due to technological hurdles and policy restrictions. In particular, chemical propulsion systems have not been incorporated on CubeSats due to the high risk they pose to their expensive primary payloads.
Manual control is accomplished through a Bluetooth mobile app, and automatic control is done with feedback from sensors.
The required precision of the design's rotational accuracy must be competitive to other existing solutions. The added ability to translate will enable this design to outperform other solutions. The system should be optimized for the allocated volume and ideally weigh less than 1.33 kilograms and at most under 1.5 kilograms. This project will be able to maneuver in 3 degrees of freedom as well as provide documentation to support 6 degrees of freedom, automatic reorientation, and stabilization. In the future, our clients would like to establish a commercial solution that utilizes the decomposing gas to propel the CubeSat in all 6 degrees of freedom. The design to accomplish this must be light, precise, efficient, modular, and reliable. We used a variety of resources in our design. All of our solid modeling and finite element analyses were performed using SolidWorks. Our control system was designed using MATLAB Simulink, and our satellite itself is controlled by an Arduino Uno programmed in C.
We used Autodesk Eagle for the electrical engineering design to make the printed circuit board. Finally, we used Python to estimate characteristics of the system and design the thrusters to be able to iterate through different versions.
In an attempt to test automatic control, the pendulum model is formed. In the pendulum model, if you move the CubeSat, gravity will want to accelerate it down to reach the final equilibrium point, the stable position. In order to counteract the force of gravity, we will be thrusting in the opposite direction in order to come to rest at a faster rate than normal.
Development of this propulsion technology has the ability to impact many different space industries. The United States government is also developing the technology through DARPA for numerous applications. The RSGS program, also known as Phoenix Project, aims to use microthruster technology on small satellites to conduct repair missions on other large satellites and stations while in orbit. This in-orbit servicing could extend the lifetime of satellites currently in use and save millions in taxpayer dollars. The scientific community is also using and expanding this technology for the purpose of exploration. The Asteria satellite, currently in low Earth orbit, is only slightly larger than a box of cereal, but uses attitude control technology to pan the sky for exoplanets by detecting wobbling stars. Overall, the continued development of this technology has a potential to make massive impacts to the industry.
3 prototypes of increasing complexity were designed, built, and tested in succession. Prototype 1 verified the functionality of the Lee Company solenoid valves, as well as basic automatic control. Prototype 2 integrated 4 valves and established manual control for the system. Prototype 3 packages the attitude control system into 1U to satisfy the client's objectives. The final design is packaged into a 2U volume for testing. The lower U holds the attitude control system, while the upper U holds the batteries. The pressure system is charged using a fill port coming out of the manifold. This feeds a single pressure system, including 4 large pressure tanks, as seen in gray. Once the system is charged and the filling assembly is removed, testing can take place. To fire the appropriate thrusters, the Lee Company solenoid valves, seen in green, are activated. Propellant is fed to them using piping, seen in white, connecting to direct metal laser sintered adapters, shown in yellow, to the manifold, which is also a direct metal laser sintered component.
The microcontroller being used is the Arduino Uno, which has the ability to update code wirelessly for easy testing. The microcontroller will be used as the trigger for the driver circuit, applying a 5-volt square wave from the digital pins of the Uno to the DRV103H chip for a controlled period of time to stabilize the CubeSat for all linear disturbances.
To simulate rotation, we used a thrust bearing, and with the proper thrusters, we were able to see enough rotational movement. So we then turned to a final pendulum design for both rotation and linear motion. This setup worked great for rotation as it offered a relatively low friction environment. However, for linear translation, we had gravity working against us. We were able to confirm manual control as well as translation accuracy and rotational pointing accuracy.
The final mass of the CubeSat is just over 900 grams, and the volume is contained to 1 U. We have demonstrated manual control using a Bluetooth connection, and progress has been made towards automatic control. The measured pointing accuracy of the system is less than 1 degree.
With many technical challenges and other hurdles overcome, the next phase of the project will begin after our departure from UVM. The next step for the design concept will be to expand to 6 degrees of freedom. This would give the final design full control and maneuverability while in orbit. Challenges will need to be overcome, such as test fixture design and component packaging, but our team is proud to have taken part in this project with Benchmark Space Systems.
This project was made possible by the Vermont Space Grant Consortium and by contributions from engineers like you. Thank you. We would like to thank Dr. Ryan McDevitt and his employees at Benchmark Space Systems, as well as Professor Darren Hitt and Ms. Deb Frazier from the Vermont Space Grant Consortium for their engineering and financial support. We'd like to thank the Space Lab here at the University of Vermont for letting us use their lab space for manufacturing as well as testing of our prototype. Lastly, we'd like to offer a final thank you to everybody that helped us out on our project in any capacity to offer advice, answer questions, and support us in any way. From all of us on Seed Team 14, thank you.
Yo!
Parakeets are stupid.
Hell yeah.